Alright, today we're going to look at current and electrons. We know that inside the metal wires, which is acting as a conductor, there are a lot of electrons, and these electrons, they are called free electrons. So free electrons mainly are because they are not bonded tightly to the nucleus. They are delocalized and they are free to move about inside the metal wires. So these mobile electrons, they actually move at a very high speed in a straight line. They collide with other electrons on their way. They move randomly throughout the conductors. So imagine like there is a field, a football field where there are a lot of children. They are running around and playing around in it. And when the bell ring is like when you connect a battery analogy, as you connect a battery to the end of the conductor. So when the children, as the electron, they hear the bell ring, then they would start to behave slightly differently. So think about that. Last time when you are playing around in the school before the bell rings to indicate that the class will start soon. So what do? So you're gonna walk slowly together with your friends towards the classroom and all that, right? So same thing about this electron. They will also behave in such that they drift. No, sorry, not this. They will drift very slowly, just like you go to the class reluctantly because that's the end of the fun time, right? So at a speed of 10 to the power negative 4, very slowly. So basically they move in such a way is because there's a signal. So this signal caused by the battery is basically an electric field. And we know that electrons, they are negatively charged. So when you apply an electric field to that, one side that become positive, let's say this side here become positive and this side become negative. So electron has a negative charge, they will be attracted towards the positive side and they'll move slowly. So not just one bunch of electron, actually there are a lot of electron on their way. So together they move slowly towards the negative side. Alright, so that movement is called the electric current. Okay, so when charged carrier move, they causes electric current. Okay, before we go further into the current caused by the movement of the charge carrier, let's look at charge itself. We know that these free electrons, they are basically carrying a negative charge, and charge is basically a property possessed by atomic particles such as electron and proton. So proton is positive and electron is negatively charged. So when these two types of charge they are placed together and they are having the same amount, basically they neutralize each other. Okay, so that's how the charge behave. And one more thing that you need to know about this charge is that it is quantized. So what does that mean by quantized? I'm going to describe an experiment in the next slide before we really talk about what is quantized means. On the top right here, that we have an experiment which is called the Millikan oil drop experiment. The details about this experiment, basically you don't have to know about that, but I'll just describe briefly about that. Okay, so there's a microscope here that is looking from here. You'll be looking into a cavity. So in this cavity here, there are some oil drops. So these are the oil drops that are released into this small hole here, and they're going to fall through it. And between that, there will be a potential difference between the two plates here, and behind here there's some backlight. Okay, that's trying to light up the oil drops. So this oil drop, they are charged. When they are charged and they move inside the electric field, so their movement is being observed and their time taken to move through that are being counted and recorded. Okay, so at the end there is a table in such that if you apply a different potential difference, that they will move at a different time and their radius can be calculated. Okay, so through these three quantities, their charge will be calculated in the last column here. Okay, so again, detail is not needed here because this experiment is basically to show you the quantization of the charge. So at the end, let's look at the last column of this table here is charge, and is 10 to the power negative 19 coulomb, and you can see some values here. Okay, now let's try to pause the video for a while, and I want you to calculate the average value of these charges that is obtained from this experiment. Right, let's pause the video for a while. Okay, so if you did some calculation, I guess you will get something like what I have written on the right hand side here, that is 35.8. That's the total. You divide by 12 lines, right, as in 12 charges as you assume, then you get 2.15 times 10 to the power negative 19 coulomb. But how exactly the average charge is calculated from the result is slightly differently. If you look at the trend here, you will see something. So let me highlight something here first. Okay, so the one that I have drawn a straight line down here, those values, you can see that they are around 1.6. Okay, so they are about 1.6, 1.62, something like that. Okay, and then there's another trend which is about 3.2. Okay, which is 3 and 3.2, and then there's one more that I highlight there, that's about the 4.8. Okay, so this experiment is repeated many times around the world by scientists. So what they form, what they obtain, basically the result are about the same. They are the trend like 1.6, 3.2, and 4.8. So what is the significance of this 1.6 and 3.2 and 4.8 is that if you do some maths calculation, you will notice that this is the factor of 1, this is a factor of 2 of 1.6, this is a factor of 3 of 1.6, and basically there are no value of the charge calculated that is lower than about 1.6. So there's no 0.9, there's no 0.8, there's no 1.2. So all these are non-existent through experiment. That means it's real. That means the result all around the world is the same. So do those value in between the 1 and 2 and 3 here. So they have no intermediate values except the average value. Okay, so which means that now we can see that the calculation could have to be done slightly differently, that we treat this as all one particle, so there are 4 here, and we treat this as 2, and this is 4, and this is a total of 3, and there's a total of 2, and there's a total of 1 here. Okay, so if you counted this, then you modify on your calculation there. Instead of dividing by 12, you divide by 16, you get something else. Okay, so you get about 1.6. Okay, so basically this is the charge of an electron, because we know that the atomizer up here, they basically squeeze some oil drop that is charged. So charge means that some extra electron is attached to the oil drop. So this electron is like in the amount of 1, 2, 3, 4, 5, and so on. And what we get in the result here show us that there's a trend of the number of them, which cause our total charge to average, the average charge to be about 1.6. So meaning that the smallest value of the charge, there's a value that's 1.6, and any value that is larger than that will be in the form of multiples. So 1.6 go to times 2 become 3.2, times 3 become 4.8, and so on. So that's basically the quantization of the charge. Alright, so that is a smallest value, and if the value is larger than this smallest value, there will be the multiples of this smallest value. Okay, so I have written down here, you can copy it down, the quantization of charge. And now let's move on. So we know that electron has charge of 1.6 10 to the power negative 19 coulombs. Alright, so what is coulomb means? There's a definition that you need to understand. Let's look at 1 coulomb. 1 coulomb basically is the amount of charge carried by 1 ampere of current flowing past a point in 1 second. okay, 1 ampere and 1 second. And we want to define the unit coulomb. We can say that it is the product of the ampere and the second. Okay, product of the ampere and the second. So Q equals to IT. Q equals IT. The charge equals to current times time. Okay, charge is coulomb. Charge is coulomb. Current is ampere, and time is second. All right. Okay, so this is a diagram showing you the 1 coulomb in such an amount moving through the conductors. Alright, then how many electrons will contribute to 1 coulomb of charge? Okay, to 1 coulomb of charge. Let's try to calculate and see. We have Q equals to NE, that this Q is the total charge of 1 coulomb, and we have the number of electron as the N, as I've written here, and E as the charge of 1 electron. So if you want to get 1 here in front to indicate that's 1 coulomb, so how many number of electron that you need? So what you can do is you just divide the 1 by 1.610 to the power of negative 19, because that's charge of 1 electron. So then you will get the total number that is needed to consist the 1 coulomb. Okay, so far we have looked at the concepts of electrons, the charge, and also the current, which is Q equals to IT, the current. I'll see you in the next video. Okay.